All right, so we come to an example where we can only wish that we had a log around this expression because we just learned what to do in that case. So I'm going to slide this over, and please realize you can't actually do this. I'm just going to insert in my sort of dream imaginary world here. I'm just going to imagine that there was a natural log sitting there. And if there was, I could simplify product, quotient, pull the powers down. I mean, this thing would just fall to pieces. But there's not. There's not a natural log there. And so it seems like it's only just this dream that can't really come true. Well, it turns out that sometimes dreams do come true. And so I am going to simply dream that I have a natural log, and I'm going to dream it up, and I'm going to write it down. So natural log of y equals natural log of x cubed square root of x squared plus 1 over 2x plus 1 all to the 8th. Now I can almost hear some of you protesting across the spans of time here. Some of you might be thinking to yourselves, you can't do that. You can't change the problem. Well, realize I took the natural log of both sides, and so I haven't lied. I haven't made any errors. If y equals this, then the natural log of y equals the natural log of that. There's no mistakes yet. The question is, will I be able to find dy dx? I should have written that down because that's the goal of the problem. I'm giving you this y, and I want to find dy dx. And it seems like if you take a natural log that you're not going to be able to find this. But it turns out that's not true. And so anytime there's a problem where you want to compute a derivative and having your function plugged into a logarithm would make life better, then do it. Just plug it into both sides. So here we go. I'm going to use implicit differentiation to differentiate this side. We're thinking of y as a function of x. It is a function of x. And so our formula says the derivative of ln of y is y prime over y. That's actually the only tricky part in this whole problem. If you can just remember that the derivative of the natural log of y is y prime over y, then we're good. Actually, whoa. I made a mistake. I didn't simplify before I started taking derivatives, right? So that's what we're going to do. Before we do that, though, let's simplify. The whole point of the logarithm was to simplify this before you take derivatives. So ln of y equals, let's see, 3 ln of x plus 1/2 ln of x squared plus 1 minus 8 ln of 2x plus 1. That's what you get when you use the laws of logs to rip this thing apart. If you have any questions at all about how to go from here to here, you should pause the video and work it out yourself. If you're with me, now I'm ready to take derivatives, after we simplify. And on the left side, I get y prime over y. Then I take the derivative of this piece, and I just get 3 over x plus 1/2. Derivative of the inside is 2x over the inside minus 8. Derivative of the inside is 2 over 2x plus 1. I'm done with the calculus, and in order to solve for y prime, what do? You simply move the y back over and multiply the whole thing by y. I'm going to go up and copy what y equals and put it back in terms of x. So I know that y prime is y times 3 over x plus, let's cancel these 2's. So plus x over x squared plus 1 minus 16 over 2x plus 1. And that's it. That's your y prime. And so this is a really handy technique. It's called logarithmic differentiation. And anytime you do that, anytime you take the natural log of your function, as long as you take the natural log of both sides and do logarithm and do implicit differentiation on the one side with just y, then you can always recover dy dx. And so I'll do one more example in this video. We can finally prove the power rule. Let me just show you how to do that. So we have y, here, let's slide this up. We have space. We have y equals x to the n. And so I can say, well, ln of y is ln of x to the n. And I can write that as n ln of x. And so now I can take derivatives. And so I get y prime over y equals n times 1 over x. Or if you want, just n over x. And so that means that y prime is y times n over x, but y is x to the n. So I get x to the n times n over x, which is exactly x to the n minus 1 times n. And so the point is, I'll write it here, y prime is n times x to the n minus 1. And so that actually works for, we think of n as a natural number. This actually works for n being any real number. And that's how you prove it. So a really nice way to be able to do that. All right, well, let's break this video here, and we will continue in the next video.